acceleration of a circular motion. Now, is there an acceleration for a circular motion? Well, in the beginning, when I was demonstrating the motion of that metal ball, I showed you why the metal ball goes in a circle. Because there is a force pulling it towards the center. If there is a force pulling it towards the center, that force must produce an acceleration. In fact, you remember the example of the student I gave you, a student who is running along a straight line. Now, the moment I catch hold of him, I am changing his state of motion. And according to the laws of motion, the state of motion can be changed only if you apply a force. And the moment you change the state of motion, you are creating an acceleration. Whenever there is an unbalanced force, you create an acceleration. Now, an object can be kept moving along a circle only if there is a force that exists that is directed towards the center. And as long as that force exists, there will be an acceleration. That means the moon is accelerating towards the earth continuously. The earth is accelerating towards the sun continuously. You see that? The moon is falling towards the earth with an acceleration. And that is the only way it can keep going round and round. It doesn't fall, means it goes away. Okay. Velocity is a vector quantity and it has magnitude and direction. So, if we talk about the velocity of an object moving along a circle, although the speed can remain a constant because the direction of motion continuously changes, the velocity of an object moving in a circle is continuously changing. It can have a constant speed, but its direction is continuously changing. That means the velocity is changing. So an object moving around a circle has a continuous acceleration, and that change or that acceleration is produced by the force that is directed towards the center. Now, since the direction of motion of an object in circular motion is changing continuously, its velocity changes continuously. Now, when the object is at B, what is the direction of its velocity? At any given instant, the velocity of the object in circular motion is along the tangent. So, if I have the object at B now, if the force acting towards the center will cease, the object will go towards the tangent. That is the direction of its velocity. If the object is at A, its velocity will be directed along that tangent. When the object is here, its velocity will be directed along that tangent. In other words, the velocity of the object at any point along the circle is along the tangent. And if you notice, the length of these arrows are all the same, indicating that the speed is a constant. The rate at which the distance covers is a constant, but the velocity is not a constant. Why? Because the direction is changing continuously, so the velocity changes although the speed is a constant. Okay, the direction of velocity at any instant is along the tangent at that point drawn to the circle. At the point A, the velocity is v1. At point B, the velocity is v2. Now, look at the lengths of the arrows. If you notice, if I can measure the length of the arrow here, and the length of the arrow there. The length of the arrow in both cases is the same. What does it indicate? It indicates that the magnitude of the velocity is the same in both cases. So what is different? What is different is the direction. The magnitudes of V1 and V2 are the same. Now, V1 and V2 differ only in direction. They have equal magnitudes. If vectors V1 and V2 are used as adjacent sides of a triangle, you know that a vector can be drawn anywhere. I can take this vector and draw it here. I can take this vector and draw it here and construct two sides of a triangle. So I'm going to use the vectors V1 and V2 to construct the two sides of a triangle. Look at this. This is my vector. Which vector is this that I have just drawn? Well, this is my vector V1. I just translated it over here. That's my V1. And where is then my V2? Look at the way I'm going to draw my V2. This is my V2. I translated this vector and kept it there. Alright, so these two vectors now represent the two adjacent sides of a triangle. Now, what does the third side of the triangle represent? The third side of the triangle then represents the change in velocity. You see, this is the change in velocity. The original velocity V1 changed to V2. The third side of the triangle is a measure of the change in velocity. So here there are three vectors. These V1 and V2, they both have the same length because their magnitudes are the same, but they have different directions. Now, what will be the angle between them? What is the angle between V1 and V2? That will be the same angle theta. Okay. Now, look at the direction of this change in velocity. Can you tell me what is the direction of this change in velocity? This velocity V1 changes to velocity V2. What is the direction of this? If I translate this vector here, you can see it will be exactly here. It is directed towards the center of the circle. There you are. I just translated this over here. You can see, but vectors, it doesn't matter where you draw it. This vector and this vector are exactly the same. So what is the direction of the change in velocity? The change in velocity delta V is directed towards the center of the circle. Why? Because the force that is causing that change is directed towards the center of the circle. Alright, what we're going to do is obtain an equation for the acceleration. Alright, let's do that using this diagram. We now join the line AB so that we have a triangle here. Look at here, there's a triangle OAB and the triangle formed by the vectors. Now, can I say that these two triangles are similar? What are similar triangles? Well, similar triangles have their angles all equal. Now, are these two triangles similar? Yes, actually they are similar. Their angles are the same. The triangle OAB is similar to the triangle formed by vectors V1, V2 and delta V. Now, what is the characteristic of similar triangles? I know some of you might remember, these are results from geometry. If you now look at this one triangle there another triangle. Well, I got to redo it. Is that right? Okay. I think I need to redo that. All right. Now, suppose this is one triangle and this is another triangle. This angle is equal to this angle. I'm going to represent like, now this angle equal to this angle and this angle equal to this angle. You see? Triangles where the angles are all equal are called similar triangles. And now, suppose I name the sides as A, B, C for the small triangle and big A, big B, big C for the big triangle. The property for similar triangles is that the ratio of corresponding sides will be equal to each other. Now, what are the corresponding sides here? Corresponding sides are sides opposite to equal angles. Now, look at this. These two angles are equal. That means small c corresponds to big C. So, if you divide small c by big C, that will be equal to small a divided by big A, and that will be equal to small b divided by big B. That is the meaning that in similar triangles, the corresponding sides are proportional. The ratio of corresponding sides will be equal. I can also say A divided by C for the first triangle will be equal to A divided by C for the second triangle. That's the same result. The ratio of corresponding sides are equal. We are going to use that over here to obtain an equation. Alright, let's do that. So, we got the triangle. These two triangles are similar. The radii OA equal to OB equal to small r, and the lengths of the vector V1 equal to the length of the vector V2 equal to V. Now, V is the uniform speed of the object along the circle. Now, in that case, this V divided by R, that is this side divided by this side, will be equal to delta V. Tell me, what is the corresponding side for delta V in that triangle? Will be AB. So V, remember, this length equal to this length equal to V. So V divided by R equal to delta V divided by AB. A very important relation. Now, when delta T is very small, this length AB is very nearly equal to the arc length AB. That is an approximation that we're going to take. When the delta T, when the time interval is very small, that means when B is very close to A, the length of this line AB is approximately equal to the length of the arc AB. Now, if V is the uniform speed during the time when the object moves from A to B, then the length of the arc AB is the uniform speed multiplied by the time. V times delta T will be the length of that arc. Is that right? Distance equal to uniform speed multiplied by time. So, we are now going to replace this AB by this quantity V delta T. So, we have V over R now equal to delta V divided by V delta T. Alright. Now, that